Welcome to Beyond the Mind. Today we begin a four-part exploration that connects an ancient maxim with some of the strangest discoveries of modern physics. The phrase is simple and memorable, as above, so below. It has been carved into talismans, whispered in alchemical labs, and used as a guiding intuition by mystics and seekers for centuries. Here, we are not taking it as a slogan or a promise. We are treating it as a question. What does this phrase actually point to, and what might it mean when translated into the language of science? Think of reality as layered. There is the scale of quarks and atoms, the scale of cells and organisms, the scale of planets and solar systems, and the vast scale of galaxies and the cosmic web. The Hermetic claim, as above, so below, proposes a mapping between these layers, that the forms, relations, or rules you observe at one level may reappear at another. That intuition has long guided spiritual traditions, but it also influenced the early thinkers who helped build modern science. Renaissance scholars and early natural philosophers did not always separate symbolic thinking from empirical inquiry. Kepler searched for celestial harmonies. Newton spent years writing about alchemy. Both operated with a worldview that took correspondences seriously. Those historical facts matter because they remind us that the impulse to seek patterns across scales is not merely mystical. It has often functioned as a method for discovering structure in nature. To move from poetic analogy to rigorous inquiry, we must convert the maxim into testable questions. Does a mechanism exist that produces similar patterns across different physical scales? Can the same mathematical structure describe phenomena that look quite different on the surface? When that happens, does the correspondence give us predictive power, or is it simply an aesthetic coincidence that delights the imagination? Those are the central questions that will guide this chapter and the series that follows. The phrase itself comes most recognizably from the Emerald Tablet, a short and cryptic alchemical text attributed to Hermes Trismegistus, a syncretic figure blending the Greek Hermes and the Egyptian Thoth. The tablet's aphorisms are compact and layered. They speak of transformation, correspondence, and the unity of opposites. As above, so below functions there as a navigational hint. Understand the macrocosm and you can read the microcosm. Understand inner correspondences and you may transform the outer world. For medieval and Renaissance practitioners, this was simultaneously metaphysical doctrine and a heuristic for experiment and contemplation. But we should not confuse the heuristic with unquestioned metaphysics. In science, analogy is useful only when it can be spelled out in mechanisms or equations. The modern way to operationalize the Hermetic intuition is to look for invariance, the symmetries, conservation laws, or optimization principles that can produce similar outcomes in disparate systems. When you find a mathematical structure that remains meaningful under rescaling or change of context, you have moved beyond poetic similarity into explanatory territory. Imagine, as a guiding mental image, a zoom lens that can sweep inward and outward across scales. Drop a pebble into a still pond and watch the concentric ripples expand. Now imagine zooming in on one ripple until it becomes a tiny wave on a petal, zooming out until it becomes an orbital path. The Hermetic maxim asks whether certain patterns survive that zoom. If they persist, why? Is persistence a consequence of the same underlying equations, shared boundary conditions, or convergent functional demands? Or is persistence only apparent, a product of the human tendency to see patterns in complexity? There are concrete scientific motifs that provide answers in different registers. Fractal geometry and scale invariance show how simple iterative rules can produce self-similar shapes across magnitudes. Information theory and the holographic principle suggest that descriptions at one level, a boundary for example, can fully encode content at another, a volume. Quantum entanglement reveals correlations that link spatially separated parts of a system in ways that challenge classical intuitions about locality. Network theory and universality explain why similar topologies emerge in systems as varied as brains, river basins, and the large-scale distribution of galaxies. Each of these frameworks gives us a distinct way to test and understand correspondence. A useful practical reframing is this: treat as above, so below, not as a metaphysical claim that everything is literally the same at every scale, but as a methodological invitation. When you see a repeated pattern, ask what invariance or constraints could generate it. Translate the observation into a hypothesis, derive testable consequences, and look for mechanisms. That disciplined approach preserves the imaginative power of the maxim while demanding the standards of evidence and explanation that make science reliable. This balance, curiosity about patterns combined with a demand for mechanism, is where the Hermetic insight and modern physics meet most fruitfully. If we keep it, we can use the maxim as a lens that sharpens our questions rather than a slogan that supplies easy answers. In the next chapter, we will zoom in on fractals and scale invariance, and we will see how iterative rules and critical phenomena can produce structures that look strikingly similar whether you measure them in micrometers or megaparsecs. For now, hold on to the image of the pebble and the ripples. Simple causes can generate patterns that invite deeper explanation, and the invitation is what we will follow together on Beyond the Mind. Walk along a coastline and measure its length with a ruler. Then measure again with a shorter ruler. The shorter ruler will usually give you a longer total length, a paradox first noticed by mathematicians studying irregular shapes. What this points to is fractal geometry, forms whose apparent complexity remains similar at multiple magnifications. The classical mathematical examples are the Mandelbrot set and the Koch snowflake. What makes them fascinating is that they are generated by simple rules, iterative or recursive processes, yet produce limitless complexity. Nature is full of fractal-like objects. Tree branches fork into smaller branches, which fork further. River basins split into streams, which split again. Lightning bolts trace branching patterns. The alveoli in your lungs form a fractal network that optimizes surface area for gas exchange. Even the distribution of matter in the universe, under some analyses and at certain scales, exhibits filamentary, network-like patterns reminiscent of fractal geometry. The physics behind recurring patterns often involves scale invariance. A system is scale invariant if its behavior looks the same at different scales. Mathematically, that means you can rescale distances or energies and the governing equations or statistical distributions remain unchanged. Scale invariance appears prominently at critical points, the precise temperatures or pressures at which matter changes phase. At the critical point, correlation lengths diverge and the system loses a characteristic scale. Fluctuations at all sizes become important. The equations governing the system near criticality often become universal, meaning that wildly different systems, a magnet near its Curie temperature and a fluid near its boiling point, for example, can be described by the same mathematical forms. Why does this matter for the Hermetic idea? Because it shows a mechanism by which similar patterns arise from very different physical constituents. The same mathematical structure, a scaling symmetry or a renormalization flow, can generate repeating forms across size and context. The correspondence is not mystical. It is mathematical and mechanistic. What looks like poetic analogy becomes a rigorous statement about how many body interactions and constraints can produce self-similar structure. Beyond critical phenomena, fractal mathematics informs approaches to complexity and emergence. The notion that local, repeated rules can lead to global patterns underlies everything from cellular automata to modern models of growth. Simple iterative algorithms apply a rule, then apply it again and again are the basic engines of fractal generation. In biology and in some engineered systems, similar iterative or recursive processes produce efficient use of resources, maximal connectivity, or optimal dispersion. In other words, the recurrence of pattern can often be traced to shared functionality. Yet we should be cautious. Not every similarity implies the same causal story. Two systems can look similar because they obey the same mathematical constraints, or because evolution and physics converge on efficient solutions, or simply because human perception favors certain symmetries. The Hermetic appeal is that it nudges us to look for these shared rules. Science gives us the vocabulary and tools to test whether the rules are genuinely shared. This brings us to a more startling modern idea where correspondence takes on a conceptual twist: the holographic principle in theoretical physics. If fractals tell us that structural similarity can persist across scales, the holographic principle radicalizes the way we think about the relationship between dimensions and information. It began with a puzzle in black hole physics. Classical intuition suggested that the information content of an object should scale with its volume. But calculations by Bekenstein and Hawking revealed that the entropy, the measure of information or microscopic degrees of freedom, of a black hole scales with the area of its event horizon, not the volume it encloses. That surprising result suggested that the maximal information content inside a region might be proportional to the area of its boundary. From this emerged the holographic principle, the idea that the physics inside a volume can be fully encoded by degrees of freedom on the boundary that surrounds it. Put another way, a lower dimensional surface could carry the information necessary to reconstruct a higher dimensional bulk. This is analogous to how a two-dimensional hologram can encode a three-dimensional image. The most dramatic realization of this principle is the AD/CFT correspondence discovered by one Meldesena, a precise mathematical duality showing that a gravitational theory in a volume of negatively curved space, anti-de Sitter space, is equivalent to a non-gravitational quantum field theory on its lower dimensional boundary. Why does this matter for as above, so below? Because here the correspondence is literal and formal. Two different descriptions, one above in dimensionality and one below on a boundary, are mathematically equivalent. It's not metaphor, it's a duality. This raises profound philosophical questions about the nature of reality and representation. If the same physical content admits two distinct but equivalent mathematical descriptions, what counts as the real description? The Hermetic maxim seems to find an uncanny scientific echo. Different levels or platforms can carry equivalent content. Quantum entanglement further deepens the sense of correspondence. Entangled particles exhibit correlations that cannot be explained by local variables alone. Measure one, and you instantaneously constrain the state of the other, even across large distances. Entanglement is now recognized not as a quirky oddity but as a resource in quantum information science, underpinning quantum computing and secure communication. Some contemporary proposals go further. They suggest that space-time geometry itself might emerge from patterns of entanglement. In these views, the connectivity and curvature of space could be a macroscopic manifestation of microscopic entanglement structure. Once again, the small-scale organization of quantum degrees of freedom shapes the large-scale geometric fabric. Taken together, holography and entanglement give concrete, testable ways in which above and below, boundary and bulk, micro and macro, can be interdependent. These are not purely metaphorical claims but formal relationships discovered through mathematics and thought experiments. They show how information, geometry, and quantum correlations can weave a tapestry where different layers of description resonate with and determine one another. At the same time, these ideas are context-dependent. The holographic dualities we understand best apply to idealized spacetimes and symmetries. Generalizing them to our exact cosmological setting is an area of active research. Entanglement to geometry proposals are tantalizing but far from being established as the final story of how space and gravity arise. The moral is balanced. The Hermetic intuition has meaningful scientific analogs, but the mapping is precise only where math and experiment support it. If the Hermetic phrase has real echoes in modern science, where does that leave us practically and philosophically? First, let's be clear about limits. Seeing similar patterns at different scales does not license sweeping metaphysical claims. A galaxy and a neuron may both be branching networks, but that similarity does not mean they share purpose or consciousness. Analogy is a source of insight, not proof. The power of seeking correspondences lies in method. Look for the governing constraints, seek the symmetries, and identify the optimization principles that can produce similar outcomes in different systems. When you find a mathematical structure, scale invariance, conservation laws, information bounds, that recurs across domains, you gain conceptual leverage. That leverage is practical. Engineers exploit fractal and scaling ideas to design efficient antennas. Physicists exploit holographic dualities to compute quantities that would otherwise be intractable. Computer scientists borrow network theory to model both social interactions and protein folding. There are also ethical and existential implications. If patterns repeat across scales, then small changes in local rules can sometimes produce outsized effects in large systems. That's a lesson for policy, for organizational design, and for personal growth. Micro-level habits can aggregate into macro-level culture. Local design choices in algorithms can produce global bias. Recognizing correspondence encourages humility. We must treat analogies as tools for exploration, not carte blanche for mystical projection. Finally, there is a spiritual or psychological dimension that remains valuable, even when stripped of metaphysical claims. The Hermetic maxim can function as a poetic shorthand for a way of paying attention, an orientation toward patterns, interconnectedness, and layered explanation. It invites curiosity and a style of thinking that moves between scales, that treats the world as a network of relations rather than a set of isolated things. So how to conclude? As above, so below began as a metaphysical insight pointing toward correspondence between levels of reality. Modern science has translated that intuition into concrete frameworks. Fractal mathematics and scale invariance show how patterns recur. The holographic principle and entanglement reveal formal correspondences between descriptions. Network theory and universality explain why similar topologies emerge in systems as different as brains and galaxies. These parallels do not collapse the distinction between metaphor and mechanism. Instead, they refine the Hermetic claim. The world contains repeated structures because shared constraints and deep symmetries often govern systems at different scales. If there is a single takeaway, it is this: look for the math, seek the mechanisms, and remain open to wonder. Correspondence is not a substitute for evidence. It is a lens that helps us ask better questions. That lens has guided mystics and scientists alike. And in our time, it continues to point toward fertile ground where the ancient and the modern meet. Thank you for listening. If you found this script useful for your video, feel free to adapt the language and pacing to your own voice.